Welcome back to the deep dive. Okay, let's unpack this. Today we're diving into something really specific and crucial for many of you. It's part of our CSWIP 3.1 exam prep series. We're aiming to help you get ready for that CSWIP 3.1 Welding Inspector Exam. We'll be working through some multi-choice questions, but it's not just about spitting out answers. We want to dig into the why behind them, clarify the key ideas, and really help solidify your understanding so you're set up for success. And here with me is our expert, ready to give us those core insights we need.
Glad to be here. And yeah, this kind of detailed prep is just so important. Understanding the principles behind the facts, that's what makes an effective inspector. It's not just about the exam, it's about real-world application.
Absolutely. Well said. It really highlights why this matters.
Yeah.
So, okay, let's jump right into the first question, trying to think it through as we go. Question 1 is, a crack running along the central line of a weld bead could be caused by. Your options are A, use of damp flux, B, lack of preheat, C, arc voltage too high, or D, weld bead too deep and very narrow. Just take a second. Picture that weld bead. What causes a crack right down the middle? Okay, the correct answer here is D, weld bead too deep and very narrow.
Right, and what's interesting here is how that specific shape, that geometry, leads directly to this type of defect, a deep and very narrow bead. Well, it solidifies in a particular way. Think of it cooling from the sides inwards. The very last bit to solidify is right down that central line.
Oh, okay.
And as it cools and shrinks, it gets pulled apart, basically. Huge tensile stresses build up right there. If the stress is too much for the metal at that temperature, especially if it's prone to it, pop in, you get a centerline crack. Solidification cracking, that's the term.
So that direct link between the shape and the crack, it really highlights how critical process control is. It's not random.
Not at all.
So for an inspector, seeing that kind of deep, narrow profile should be a big warning sign, right? It signals potential trouble.
Exactly. It points to how the weld was made.
What kind of adjustment would prevent that? Like for the welder? Is it speed, current?
Good question. It's usually about balancing things. That shape often means too much heat packed into a small area, maybe moving too fast. So you might need to, say, lower the current a bit, maybe slow down the travel speed. Sometimes adjusting the voltage can help widen the bead.
Okay.
You're aiming for a better width-to-depth ratio, something less peaky, to reduce those stresses in the middle as it cools. Tiny changes, big impact.
Right, process control. Got it. Okay, let's shift gears slightly. Let's talk about what happens inside the metal, the material properties. Question 2. A large grain size in the HAZ of a CMN steel weld joint may have your options A, low ductility, B, low toughness, C, high toughness, or D, high tensile strength. Think about the heat affected zone, the HAZ. What happens when those grains get big in standard carbon manganese steel? The correct answer, it's B, low toughness.
Yeah, the AKZ. It's that zone right next to the weld that didn't melt but got seriously hot.
Right.
In CMN steel, your everyday structural steel, if those grains grow large because of the heat cycle, it directly impacts toughness. Specifically, it leads to low toughness. And low toughness, well, that means the material can't absorb much energy before it fractures. It becomes more brittle.
More brittle, okay.
Which is bad news, especially if the part is going to see impacts or operate in the cold. Risk of brittle fracture goes way up.
So for you as an inspector, spotting signs that might indicate a large grain size in the HAZ or knowing the welding conditions could lead to it, that's crucial for judging if the part is actually safe.
Absolutely vital. The HAZ is often the weak link. Understanding how welding heat affects its microstructure, things like grain growth, is fundamental.
So what are the implications then? If you suspect a large-grained HAZ, what happens next? Is it about design or maybe treatment after welding?
Well, it depends. If it's a critical application, especially low temp or dynamic loads, it's a major red flag. You might need post-weld heat treatment, PWHT, to try and refine that grain structure or at least temper any brittle phases.
Ah, like an annealing process.
Sort of, yeah. Or you might need more testing. Maybe ultrasonic testing or even destructive tests like Charpy impact tests on representative samples to directly measure the toughness.
Okay.
It really forces you to verify the actual properties, not just assume they're okay based on the welding procedure, especially if control was maybe a bit loose.
Makes sense. You're looking beyond the surface. Okay, let's talk about a technique inspectors use to actually see inside the weld. Question 3. A macro section is particularly good for showing are A, the weld metal HAZ microstructure, B, overlap, joint hardness, or D, spatter. Think about what a macro section is. A slice through the weld, what does it show best? The correct answer here is B, overlap.
Yeah, different tools for different jobs, right? A macro section, you cut the weld, polish it up, maybe etch it.
You get a cross-section view.
Exactly. A magnified look at the whole weld profile. And it's fantastic for seeing macroscopic things, geometric things like overlap. Overlap is where the weld metal just sort of spills onto the base metal surface, but doesn't actually fuse properly. It creates a kind of lip.
Like it didn't wet the surface correctly.
Precisely.
Right.
And because it's a shape issue, a visible flaw on the cross-section, the macro section shows it clearly. No ambiguity.
Okay, let's unpack this. A macro section is a simple but really powerful tool for confirming something like overlap. It's like getting visual proof.
It is.
What kind of welding mistakes usually lead to overlap? What would make an inspector say, okay, let's do a macro on this?
Often it's related to technique or parameters.
Well,
Maybe not enough heat for the speed they were traveling, or the electrode angle was wrong, or they tried to put too much metal down at once, especially if it's not flat. The putter just doesn't fuse, it rolls over. So finding overlap in a macro isn't just finding the flaw, it tells you something went wrong with the process, current, speed, technique. Gives you clues.
it's like reading the weld's history.
Okay, interesting. Let's move to something preventative now, a really key practice. Question 4. Preheating a low-alloy steel prior to welding will minimize the risk of choices: A, porosity. B, excessive distortion. C, HAZ cracking. Or D, lack of fusion. Low-alloy steels. What are they prone to? What does preheating help prevent? The answer you're looking for is C, HAZ cracking.
Yes, this gets to a really fundamental preventative measure. Preheating, especially for low alloy steels, is primarily done to minimize the risk of HAZ cracking. You see, these steels can be susceptible to hydrogen cracking and also to forming brittle microstructures if they cool down too fast after welding.
Hydrogen, right, from moisture.
Often, yeah. Moisture in the consumables on the plate. Preheating does a couple of really important things. One, it slows that cooling rate right down. That slower cooling gives any hydrogen trapped in the metal more time to diffuse out harmlessly instead of causing cracks.
Okay, gets rid of the hydrogen. And second, slower cooling means you're less likely to form those really hard, brittle structures like untempered martensite in the HAZ. You get something tougher, more ductile. Plus, it reduces the thermal shock, the stress from the temperature difference.
So it tackles multiple potential problems at once. It really sounds like preheating isn't optional for these steels, it's essential engineering.
For many low-alloy steels, absolutely. It's often a mandatory requirement in the welding procedure specification, the WPS.
Is there a specific temperature or does it vary? What does an inspector check for?
Oh, it definitely varies. Depends on the steel's thickness, its specific alloying elements, the welding process. It's all laid out in the WPS. The inspector's job is to verify that the specified minimum preheat temperature is actually achieved, usually using temperature indicating crayons or pyrometers, and that it's maintained during welding.
And if it's not done right or
That's it.
skipped?
Big trouble. You risk immediate cracking in the HAZ, maybe even before the weld is finished cooling. It severely compromises the joint's integrity. Could lead to failure down the road. It's a critical check.
Definitely sounds critical. Okay, proactive quality control right there. Let's tackle our last question for this session. This one's about consumables and process specifics. Question 5. Which of the following is a suitable shielding gas for FCAW of stainless steels? Options are A, 100% argon. B, 70% argon plus 30% helium. C, argon plus 5% hydrogen. Or D, argon plus 20% CO2. FCAW flex cord arc welding on stainless. Which gas works? Okay, thinking caps on. The correct answer is D, argon plus 20% CO2.
Right. This really gets into the specifics, doesn't it? FCAW on stainless. The shielding gas choice is very deliberate. Now, the flux inside the wire provides a lot of the shielding, but often an external gas is used too to improve things. Arc stability, weld pool protection, bead shape.
So it fine-tunes the process.
Exactly. And for stainless steel FCAW, that argon plus 20% CO2 mix is a very common, very effective choice. The argon gives you good arc stability. The CO2, even though it's technically reactive, adds a bit of energy, helps with bead wetting and shape, often gives you a nicer spray-like transfer.
But CO2 isn't bad for stainless in this amount. Doesn't it cause oxidation?
That's the key, the amount. At 20%, it provides benefits without causing excessive oxidation or leading to significant carbide precipitation, which would hurt the corrosion resistance of the stainless steel. It's a carefully chosen balance.
So what does this all mean? This specific blend, it's another example of how precise welding needs to be. It's not just any gas will do.
Absolutely not. Using the wrong gas here could really mess things up.
Like what if someone mistakenly used, say, 100% argon? Or a mix with way more CO2.
Well, 100% argon with a wire designed for a mix might give you a really erratic arc, poor fusion, maybe porosity. It just wouldn't run smoothly.
Yeah.
And if you went with too much CO2, say 100% CO2, that would definitely be too oxidizing for stainless. You'd likely lose corrosion resistance, get poor appearance, maybe metallurgical issues like sensitization. So that argon plus 20% CO2 hits a sweet spot for many stainless FCAW applications. Again, for the inspector, job number 1 is checking the gas cylinder and flow meter against what the WPS demands. Using the wrong gas invalidates the procedure.
It really underscores how every detail matters. Matching gas to process to material, that's crucial knowledge.
Wow. Okay, so just to recap quickly, we've covered quite a bit. Centerline cracks linked to that deep, narrow bead shape.
Right, the geometry.
Then large HAZ grains in CMN steel, meaning low toughness.
The brittle wrist.
Using macro sections specifically to spot overlap.
Perfect tool for that job.
The absolute necessity of preheating low alloy steels to prevent HAZ cracking.
Can't skip that.
And finally, knowing that specific argon plus 20% CO2 mix is the go-to for a lot of stainless steel FCAW.
That precise consumable choice.
Each of these points, understanding them, it's not just for the exam, is it? It builds that practical foundation you need out in the field, ensuring safety, ensuring quality. So thanks for joining us on this deep dive. Keep digging into these concepts. This detailed understanding is what makes a really skilled, really competent welding inspector. And maybe one final thought to leave you with as you continue studying, try to connect these dots. Don't just memorize preheat prevents HAZ cracking. Think about how these things interact in reality. For instance, how might a little bit of overlap, maybe missed during visual inspection, create a stress riser right at the toe of the weld?
Okay.
And what happens if that area also has a coarse-grained, low-toughness HAZ because maybe the preheat wasn't quite right? You see how these factors can compound?
Yeah, it creates a perfect storm for failure.
Exactly. Thinking about those interactions, how one thing affects another, that's moving beyond just knowing the answers. That's developing real inspection insight. That's the goal. Keep connecting those dots.